Hi, this is Matt Hill from the Johns Hopkins University Applied Physics Lab. This is the full-length talk on considerations regarding galactic cosmic ray measurements for an interstellar probe type mission. I'd like to thank my co-authors for their input, but I should point out that I have not given them a chance to see the final product, so any errors are my own. So I'm going to start by talking about some interesting GCR Science topics that we could address. One would be looking at the amount of modulation of GCR as it happens in the helium sheath. Quite a large fraction of it takes place there, so this is something that should be studied. Additionally, we need to study the heliopause crossing in higher temporal resolution and with complete coverage. This means that we'll need to measure the data at medium or high time resolution, better than sort of a minute scale, so we can capture this information at the heliopause and also at the termination shock. Most of the data that we take will be returned at low time resolution, let's say on the order of an hour, but when we cross these boundaries, we will need to return the high resolution data in order to adequately study the crossings. We also want to look at the GCR variations associated with magnetic field variations when there's, for example, a passing traveling shock, and we might use a scientist in a loop sort of method to also get higher resolution data for those kind of periods. So out in the local interstellar medium, the heliospheric particles go away, and this makes it possible for us to measure galactic cosmic rays down to much lower energies than before. We can see here in the Voyager data, which is we've adapted from Cummins et al. 2016. You can see galactic cosmic rays are measured down to a couple MeV per nuke, which is already way below what was done before. And we should be able to, with the new instrumentation on an interstellar probe kind of mission, go down to much lower energies than this, with higher quality measurements down to dozens of keV or so. And this is important because we can study how there are spatial gradients that might show up in these low energies. They don't appear to be showing up at the energies that we can measure with Voyager 1, but perhaps down another factor of 100 or so in energy, we'll be able to see them. And there could be temporal variations as well that we can see that currently are not being observed. So anisotropy measurements of galactic cosmic rays ended up being surprisingly very important. Kremidis et al. In 2013, using Voyager 1 LACP data, found second-order anisotropies in the galactic cosmic rays greater than 200 MeV particles. In measurements similar to these are actually from Hill et al. 2020, but they saw in the intensities that are perpendicular to the magnetic field, there was temporal variations, these long episodes that are sort of hundreds of days, whereas parallel to the magnetic field, the cosmic ray intensity stayed pretty constant. In the Hill 2020 paper, we talk about how these anisotropies could result from a disturbance that leaves the heliosphere in the draping region. Galactic cosmic rays enter this trapping cooling region behind the shock, and there's a preferential decrease in intensities perpendicular to the field, and when they escape and flow towards Voyager 1, this anisotropy imprint is retained. And this would allow for the anisotropies to take place even when the shock is not at Voyager 1. And this is important because we do see that the anisotropy episodes don't coincide with the in situ measurement of the shocks. More on anisotropies are looking at other energies and other species. For example, in a paper from 2020 by Rankin, McComas, and Swedren, they looked at GCR electrons, and they found, interestingly enough, that the anisotropy did not exist for electrons. So that needs to be explained. And here, in a paper that's in development by Nikukar et al., and also there's a talk in this conference, we're looking at lower energy galactic cosmic rays down to 7 MeV or so, and also breaking up the measurements into smaller energy bands so we can look for energy dependence. And so what you can see here in this example is the ratio of the perpendicular to parallel GCR intensities. And what you can see is that the different colors here refer to different energies, and that the ratios, and thus the anisotropies, do have an energy dependence. We're going to use that to constrain which physical processes could be responsible for the anisotropy episodes. And in addition, another interesting topic is looking at GCR isotopes. And this allows us to observe cosmic ray clocks, and the decay lifetimes allow us to determine when and where cosmic rays are produced. And so this is a topic that should be addressed by an interstellar probe mission. So let's talk about some of the existing instruments that are flying already. Here is low energy charged particle instrument, Cremidis et al., 1977. This is not primarily designed to be a cosmic ray instrument, but it ended up being the instrument that discovered the local interstellar medium anisotropy episodes. So even though it wasn't designed, it was designed more for lower energies, in one of the higher energy channels, because of we detected the anisotropy, and this is because we used a stepper motor, and that rotates 360 degrees, and this was able to determine discover this anisotropy, which was otherwise not seen. So this is trying to highlight the importance of an anisotropy measurement. The CRS instrument, Stone et al., 1977, is a dedicated cosmic ray instrument and has high energy response and energy resolution and composition, and it has a number of heads at different angles, but because of the lack of dedicated anisotropy measurements, it was only later that the CRS instrument was able to detect indications of the anisotropy, and then this was done by using the omnidirectional guard ring rates, and then also later, additionally, they looked at periods during magnetic rolls, and also were able to confirm these anisotropies. So a interstellar probe instrument would need to have the energy and composition at capabilities of high energies and anisotropy determination built in from the beginning. The CRS instrument from ACE is a large instrument, 29 kilograms, so too big for something like Interstellar probe, but I'm using it here to highlight that isotopic measurements can be made. In this case, one of the things that makes the isotopic measurements possible is the scintillating optical fiber trajectory hodoscope. This gives the trajectories of the particles so that when the energy deposit is made in each of the layers of the detector stack, then the angle of incidence is known, and so that there can be a proper determination of the species. And you can see here in this plot, various isotopes are shown and can be distinguished. There would need to be a small, lower mass method for doing this for an interstellar probe sort of mission. And here, just quickly showing Parker Solar Probe ESIS Suite Epi-High instrument, which is a instrument that measures cosmic ray energies, and it's doesn't have the isotopic resolution that CRS does, but it is also at a much smaller footprint with a little over 4 kilograms and less than 7 watts of power. So before talking about what goes into the measurement requirements, just going to give a quick description of the spacecraft spin orientation. You can see here's a notional interstellar probe with an octagonal spacecraft body, and this is being redrawn here diagrammatically. And the spacecraft would spin about this spin axis, the direction shown in blue or by the red spin axis. If you look at the side, you can see that there would be an instrument mounted on the deck or on some sort of boom attached to the deck, and one measurement in the elevation angle or along the axis, there would be nothing the spacecraft does that would provide that information, so that the instrument would have to determine measurements coming in at various angles. So in other words, there need to be angular resolution in the elevation direction. But if you look over, looking at the anti-sun deck, you can see that the spacecraft will be spinning, and if the instrument is staring up, then the azimuth will be swept out by the spacecraft spin. So there'll be no need to add any special instrument capabilities to measure anisotropies in the azimuthal direction. So measurement requirements, there'll be requirements on intensities that won't be very strict because GCRs don't vary that much, so that won't be hard to meet. Anisotropy, which is important in the LISM, this will mostly be handled by the spacecraft spin, but there will also need to be some 1D angular resolution. Composition, this is for the isotopic studies. One way to handle this, we'll discuss two ways of handling this, either with a single sensor that has detailed position sensing information, or with a separate dedicated sensor for the higher mass resolution measurements. Most of the time, medium time resolution would need to be used. If we have the spacecraft making measurements on the order of a minute, then that should be sufficient, and for most cases, and for example, crossing of the termination shock of the heliopause. But for most of the time, outside of those special cases, we'll be able to do longer time averages, and this will save on telemetry. And I also mentioned here in number 5 the possibility, especially if we have a separate isotopic telescope, we could also consider adding an electrostatic analyzer to get charge state information, although there will be limitations based on the energies, what energy range we can get charge state, but it might be possible if we have a separate sensor. So first, talk about the single sensor method. This method would be an approach where we use multiple identical heads. In this case, I'm showing two, a sort of fore and aft head. This is what each one looks like. One looks in the fore direction and one looks more in the aft direction, but they'd be the same. They would have high angular resolution by using position sensing, and this would also enable the instrument to make good mass determinations. It would be a trade-off, and this would be more technically challenging than the approach I'm going to show next, because you would have to have your background kept down. You'd have to make sure that the position sensing is very precise. This would probably be a more costly approach that would end up resulting in a lower mass than the other approach, which I'll mention here. The other approach is a dual sensor approach, in which you have one sensor with multiple heads, here shown with 5 heads, that will be the main sensor for determining anisotropy in the elevation angle direction. Again, the spin direction handles the other. And then a separate head that has a more collimated configuration, so that the particles that pass through the detectors have very little variation in the angles they pass through, and thus it's easier to get high quality mass determinations. You could always add position sensing in there too, but that makes the sensor more complicated. And I have it shown here schematically with an ESA that would enable charge states to be a possibility. Now, looking at the spacecraft from the side, with where this green eye indicates the instrument, looking close up, you see you have the main sensor mounted this direction, so the blue arrows will get the elevation angle, and then the spinning in the other direction would get the azimuthal angle. And then next to the main sensor would be the isotopic sensor. You can see it here, sort of behind the sensor from this point of view. If we look at the spacecraft from the back, you see the main anisotropy sensor here and the specialized isotopic sensor here. And this one would only get measurements that look straight out from the deck. But so no angular information other than that which is provided by the spinning spacecraft. So the important thing that we need to measure in terms of GCRs would be to make sure we get down to low energies, below a few MeV per nuke, ideally down to something like 30 keV. Using solid-state detector telescopes would work for this energy range here. The instrument should be designed from the start to make high-quality anisotropic intensity measurements. And probably the best tactic would be, although it probably would be a slightly higher mass approach, but maybe it would be a simpler approach and probably better quality measurements, would be to use a dual sensor approach where we have a main anisotropy sensor and a specialized isotopic high mass resolution sensor that are different designs rather than using the single sensor approach. Thank you for your time, and I look forward to discussing this with you either virtually or hopefully someday soon in person again. Thanks.